Yeah, welcome back to the part three of my video on this topic series. And in part one, I discussed summation by parts. In part two, I discussed absolute convergence and I proved some of the theorems. In this video, I'm going to be looking at some algebra related to series. All right, so. Yeah, this was part one. I proved that the summation by part theorem, I proved this theorem in part one. I went through this procedures and also I proved the Dirichlet test using the summation by part theorem. And then I talked about the absolute convergence, the definition, and I proved that if a series converges absolutely, then it converges. But the converse is not true. I will be giving a presentation on the example why the converse is not necessarily true. So I showed this proof last video rather. In this video, I'm going to be discussing the algebra of series. Now, the topic is showing here to be the product, uh, which we call Cauchy product. I'm starting from the product because conventionally, if you have two series, if I have sum of an plus pn, I can split it to be sum of an plus sum of bn. The same thing with addition or subtraction, the same thing with scalar multiple. But when it comes to the product, then we have something different. So in this definition, if I am giving a series, sum from n equal to 0 to infinity of an and sum from n equal to 0 to infinity of bn. The product, which is tagged Cauchy product, is the series sum from n equal to 0 to infinity of cn, where cn is given by another series, which is sum from k equal to 0 to n of ak bn minus k, n starting from 0 to infinity. Now, notice that this is not just, the product is not just the sum of an times bn. I emphasize this in the summation by parts expression that I gave in my first video. Again, this is the third video on this topic. All right, so let's see, although this is definition, but let's see how the intuition behind defining the product in this way. And I'm going to be using simple case of power series. We have discussed all about power series in the previous topics that we dealt with under series. So consider two power series in this form, sum from n equals to 0 to infinity of an z to the n, and sum from n equal to 0 to infinity of bn z to the n. So what are we going to be doing? If I multiply these two series together, and I write it out explicitly because these are power series, so it is a polynomial in Z, infinite polynomial. So I will have A0 plus A1Z plus A2Z squared plus all the way multiplied by B0 plus B1Z plus B2Z squared all the way. And of course, you want to open up the parentheses term by term. This is infinite, so we can just write out the first few terms. So A naught times B naught obviously is the first one. If I use A naught times B1 of Z, and I have A1 Z times B naught, that will be the term that will be given by the z. So I'm going to have a naught plus b1 plus a1 b naught all multiplied by z. You can do similar thing for the z square and so on and so forth. So we can collect all the expressions in like terms and put them all together to have the power of z. And each coefficient, I call them C naught. So for example, A naught, B naught is described as C naught. A naught, for the second coefficient here, is described as C1, and so on. Now, if I do this, so the product naturally is given by this. Now, let's take the original series that we have from the definition of Cauchy product. What happened to this series if I begin to expand it? C0 is going to be when n is 0, so that will be sum from k0 to 0 of a, k, b, 0 minus k. Obviously, this is just a single term because k is moving from 0 to 0, and that would be a0, b0, which correspond to what we have when we expanded that term. Second one is C1, which is k equal to 0 to 1 of ak b1 minus k. Again, so these are two terms. So when k is 0, I will have a0 b1 minus 0, which is b1. When k is 1, I will have a1, then b1 minus 0 minus 1, which is b0. And you will get this term. If you do the same thing, this is a typo. This should be C3. You will get this, which corresponds exactly to what we have in the other side. So if we take Z to be 1 in the power series product in the previous slide, so remember that we had Z to the N here, Z to the N here, and Z here, Z square here. So Z is 1 means that the Z disappear here and the Z disappear there, and then all the Z, you can no longer find them. And then obviously this is now the C0, the C1, the C2 as we have expressed. And then I have the sum from n equal to 0 to infinity of Cn, where Cn is given like this. So this is the intuition about defining the product of two series this way. Now let's look at the theorem. So the idea is that under which condition can we say the product of two series converges? All right, so first assumption is that one of the series has to converge absolutely. I'm going to emphasize this later on. So assuming that series AN converges to A, the series BN converges to B, and Cn is given as this, then the product of the series AN and the product of series BN, which is the series Cn, converges to A times B. If the first condition is not satisfied, we cannot guarantee the convergence of the product. In other words, you cannot say that if the series AN converges and the series BN converges, then the product of this series will converge. That is not necessarily true. I'm actually going to show an example where that is not necessarily true. However, if at least one of these series converges absolutely, then the product of the series will converge. That's a condition. At least one has to converge absolutely. All right, so this is the remark that I just spoke about. The product of two convergent series is not necessarily convergent. If neither converges absolutely, that's exactly what I just explained. At least one of these has to converge absolutely before we guarantee that the product converges. And an example is this. So let's define our an to be minus 1 to the n over square root of n and bn to be the same thing. Previously, we have shown that these two series converges. These two series converge by alternating series test. We have shown this in our previous discussion. So we saw that both of them converges. Now, the challenge is to check if the product converge. All right, so by the Cauchy product, we can write the Cn to be sum of AK Bn minus K. I just multiply these two sequences and change the indexes. And then the next thing to do now is to estimate what is in this is in the sum. Now, observe that minus 1 to the k is multiplying minus 1 to n is multiplying minus 1 to minus k. So minus 1 to k times minus 1 to minus k is going to become 1. And the only term that survives in the numerator here is just minus 1 to n. That is not dependent on k any longer. We can put it out of the sum. And so that is how we obtain this next expression here. So we have minus 1 to n is out of the sum. Minus 1 to k times minus 1 to minus k gives you 1. And the denominator both have the square root, so we can combine them in single square root. So what is next again is to estimate 1 over square root of k into k minus k, n minus k. Now, so let's go into that estimate. What is very nice about this video is that I show step by step of how this estimate is done, so that it's not confusing at all. Now let's start from what is inside the square root at the denominator. So we have k into n minus k. Of course, we can open the parentheses to have nk minus k squared. The goal is to complete the square, so I'm going to write it like a quadratic stuff. So that's why I'm pulling out the negative so that I can interchange the term. So I have k squared minus nk inside the parentheses. And if you don't forget how to complete the square, divide the middle term by 2 square and add and subtract the term. So that's what I'm doing here. The middle term here, the middle coefficient here is minus n. So I divide it by 2, I square it. So in this case, I just add it and subtract from both sides. Now, elementary mathematics, the first year undergraduate, we understand that the first expression here can be written as a perfect square. So it will be k minus n over 2 all squared. Why this last expression is being kept here? This is a typo. This is n squared over 4. Please take note of that. This is n squared over 4 because 2 squared is 4. Minus n squared is n squared. All right, so because of the negative outside, I can interchange them back so that I have n squared over 4 minus this square. Of course, this second term here is positive because it has a square. So if I'm subtracting a positive number from a term, that is going to be less than that term. Imagine you have 5 and you're subtracting 1. 5 is minus 1 is less than 5 itself. So this is a number and we're subtracting a positive number, so that number is going to be less than it. So what we have shown so far is that k into n minus k is less or equal to n over 2 all squared. That's a very good estimate. Therefore, if I take the square root on both sides, right? Notice that they are both positive. So if I take the square root on both sides, I'm going to have square root of this less or equal to the square root will cancel out the square. So I just have n over 2 in this case. And of course, I need the expression inside the sum is 1 over that. So if we take 1 over this piece, it will be the inequality will switch to bigger or equal to 2 over n. You interchange the other side of you interchange the fraction. Now, if I take the absolute value of the expression we had in the previous slide, which is this absolute value of this sum, I can use triangle inequality. I don't think I need that even in this case, since I've already estimated what is inside the sum. I know that that is bigger than this piece. So, and this is, of course, positive, so I don't need the absolute value any longer. Notice that this expression has nothing to do with k, so since it's not dependent on k, I can pull it out of the sum. So what I'm actually doing is to sum 1 in n times. If you sum 1 n times, what you will get is 2 over n times n. And in this case, you just get a 2. So eventually, what we have seen here is that the Cn cannot convert to 0 because for all n, this is bigger than or equal to 2. Remember, for Cn to convert to 0, absolute value of Cn has to be less or equal to epsilon for all n bigger than or equal to capital N. So, but that is not the case here. That means if Cn does not convert to 0, we know from the previous theorem that the series given by Cn cannot converge. So this series diverges. Again, we started by giving the examples where we have two series, both converges, but eventually the product does not converge. The catch here is the two series none of the series converge absolutely. None of the series converges absolutely. And that is easy to see if I can go back a little bit. If you take absolute value of an, you are going to have 1 over square root of n. The series, the sum 1 of 1 over square root of n does not converge because it is a p series where p is 1 over 2. So absolute convergence is not with each of these series, the series given by this an and bn, each of them does not converge absolutely. That is why the products end up not being converges. As an emphasis, if two series converges, if we have two series and they both converge, we are not guaranteed that the product will converge, except if one of them converges absolutely. All right, I'm going to stop this video at this point. I'm going to be making the fourth video. Watch out for that. That will be on rearrangement of terms. Thank you very much for watching.